Hello everyone, and welcome to my first video tutorial designed to help you prepare for success in anesthesia school. Do you enjoy math? Well, if you don't, you're not alone. There's literature that tells us that registered nurses notoriously don't like math. Now, I expect that some of you do enjoy it, and you're not at all intimidated by the thought of having to perform medication calculations on the spot in the operating room. But my 15 years of experience teaching nurse anesthesia students has shown me that the literature is correct. Many of you are intimidated by math. So I've prepared this video and some practice problems to help you brush up on your math skills before you start the program. What about the second question here? Are you confident in your ability to perform basic drug calculations in your head? There are calculators in most anesthesia carts, and most nurse anesthesia students carry a calculator with them in a clinical area. But calculators fail and batteries die, so we have to be able to perform routine medication calculations in our head. Clinical instructors will expect you to be able to do this. So I recommend that you practice the examples in this video and the practice problems that I've posted to the website so that you're comfortable with the math involved in anesthesia prior to starting the program. It will save you valuable time during your first semester, I assure you. One thing you'll learn about me very early in the program is that anytime I have a memory aid or a trick that can help make things easier for you, I will share it with you. So as we go through this video, I will share a few tricks and memory aids to help you with the math. It's no surprise to any of you that there are 4 principal mathematical operations: addition, subtraction, multiplication, and division. But did you remember that there's a specific order in which these operations should be performed? The phrase, "Please excuse my dear Aunt Sally," will help you remember the correct order of operations. The first letter in each word in this phrase represents a mathematical operation that begins with the same letter. Therefore, in an equation that has multiple operations, anything in parentheses must be done first, followed by exponents, multiplication, division, addition, and finally subtraction. An example where the order of operations is important is on the slide. You will be asked to memorize the formula for converting temperature from degrees Celsius to degrees Fahrenheit. If the operations in this equation are not performed in the correct order, you won't come up with the correct answer. So to illustrate this point, I'm going to bring in my calculator, and we'll work through the equation the first time just from left to right without regard to the correct order of operations. So I'll start by plugging in 37 degrees Celsius times 9 divided by 5 plus 32. Just by proceeding through the equation from left to right, we've determined that 37 degrees Celsius is equal to 98.6 degrees Fahrenheit, which we all know to be the correct answer. You may wonder how this happened since we didn't pay any attention to the correct order of operations. Well, let's take a look. Order of operations tells us that we should perform anything in parentheses first. There were no parentheses. So you move on to exponents. There were also no exponents in this particular equation. Multiplication comes next. Did we multiply first? Yes, we did. We started with 37 degrees Celsius times 9. Following multiplication comes division. Did we divide next? We did. After we found the product of 37 degrees Celsius times 9, we divided it by 5. Then we added 32. Which, following our order, is the next step. Subtraction is last. There was no subtraction in this particular formula, so it just so happened that this formula was set up so that you could perform the operations from left to right and indeed be following the correct order of operations. I can assure you that not every formula will be set up so that you could just perform the operations from left to right and still come up with the correct answer. So to illustrate what happens when you do not perform the mathematical operations in the correct order, let's start by adding 5 plus 32 this time. 5 plus 32 equals 37. I'll submit that to memory. Then we'll go back and do the 37 degrees Celsius times 9 The next operation in the formula is division, so we'll divide, but we've already added the 5 plus 32, so I'll go up into my memory and bring down the 37. And you see, if we did the addition first, 37 degrees Celsius would convert to 9 degrees Fahrenheit, which we all know is not the correct answer. It's not a mistake that you would want to make. So you are going to want to remember the correct order of operations. This phrase, "Please excuse my dear Aunt Sally," will help you. There are 3 different temperature scales: Kelvin, Celsius, and Fahrenheit, and in the program you will need to be able to convert between all 3 temperature scales. Absolute zero is the coldest temperature possible. It's the temperature where all molecular movement would stop. Absolute zero is equal to 0 Kelvin, negative 273.15 degrees Celsius, and negative 459.67 degrees Fahrenheit. Each one of these temperatures is equal to each other, and they're all equal to absolute zero. Keep in mind that we don't say degrees Kelvin, we just say Kelvin. Now, we don't measure our patients' temperatures on the Kelvin scale. However, in your chemistry and physics course, in the anesthesia program, you will use all 3 temperature scales, so you should practice over the summer converting between Kelvin, Celsius, and Fahrenheit temperature scales. If it's been a while since you worked with fractions, you will want to refresh your memory over the summer about how to add, subtract, multiply, and divide with fractions. Remember that if you're adding and subtracting fractions, you first have to convert to a common denominator, and then you can add the numerators. My example here is 1/2 plus 2/3. I've converted both terms to sixths. 1/2 equals 3/6, 2/3 equals 4/6. Then I can add the numerators. 3/6 plus 4/6 is 7/6, which can be simplified to 1 1/6. Similarly, you convert to a common denominator before you subtract the numerators. To multiply fractions, you simply multiply the numerators, multiply the denominators, and then simplify. And to divide fractions, you invert the second term and multiply. When working with decimals, it's important that you line up the decimals before you add or subtract. And if you're dividing with decimals and you find a decimal in the divisor, you need to first move that decimal however many places is necessary to make the divisor a whole number, then go into the dividend, move the decimal the same number of places before you proceed with your long division. When you're finished with the division, you simply bring the decimal up directly above its place in the dividend into the quotient. There is some algebra involved in anesthesia, and the algebra that we use is solving for an unknown. Remember that whatever you do to one side of the equation, you need to do to the other side of the equation for the equation to remain true. Here's a very basic example. 12x is equal to 180. To solve for x, we need to isolate x on one side of the equal sign, and we do that by dividing both sides by 12. Dividing both sides by 12 gives us x equal to 15. This is a very practical example where we use algebra, and you may find yourself using this equation several times throughout your 2 years in the anesthesia program. This is an algebraic equation used to calculate what score you need on the final exam in order to pass a course. What I've done is I've made up an example student and assigned them scores for 3 exams and a paper. And we go to the course syllabus to see how each one of those assignments is weighted. Exam number 1 is weighted 22% of the grade, as are exams 2 and 3. The paper is worth 10% of the grade, and the final exam is worth 24% of the grade. This student scored 95% on the first exam, 88% on the second, 70% on the third, and received 90% for his paper. The student is interested in knowing what score he will need on the final exam to pass the course. In the anesthesia program, the lowest score to pass any course is 82%. So you start by setting the equation equal to 82 because he would not want to score less than 82% for the course. To set up the equation, you take each score times its weight in the syllabus. So here we have the the student's first score, 95% on the first exam, times its weight in the syllabus, which is 22%. Add to that his score on the second exam times its weight in the syllabus, which is also 22%. His score on the third exam times its weight in the syllabus, and add to that the student's score for his written paper times the written paper's 10% weight in the syllabus, and add to that, here's where we put in the unknown. The unknown is the score needed on the final exam. We do know the weight of the final exam in the entire grading scheme. It's 24% of the total grade. So our equation is entirely set up. We can go ahead and solve it mathematically, rearranging to isolate x on one side of the equal sign to determine what score the student needs on the final exam in order to pass the course with an 82%. Any nurse who's given lidocaine to treat PVCs has worked with a percent solution. Fortunate for us, printed on the label, besides the percent solution, is also the concentration of the solution, usually in milligrams per milliliter. But in anesthesia, we want you to understand what that percent solution means. Pictured here, I have 1% lidocaine and 2% lidocaine. What that percent sign means is the number of grams in every 100 milliliters of the solution. So if someone hands you a 2% solution, you can remove that percent sign and replace it with grams in the numerator and 100 milliliters in the denominator. A 2% solution is really 2 grams of lidocaine in every 100 milliliters of total solution. We know that there are 1,000 milligrams in every gram, so a 2% solution is 2,000 milligrams in every 100 milliliters of solution, which can be simplified to 20 milligrams per milliliter. You will work with local anesthetics that are 0.5% solution, 1/4% solution, 1 and 2% solutions. It's important for you to understand what that percentage means when someone hands you a solution in which the concentration on the label is written as a percentage. Have you ever wondered what that 1 to 10,000 means on a box of epinephrine? Well, that's a ratio. Ratios are written with the first term followed by a colon followed by a second term, and when you speak it, the colon is read as the word 2. So in this instance, we have a 1 to 10,000 solution. What that means to you is that there is 1 part of epinephrine in every 10,000 milliliters of total solution. Or there's 1 gram of epinephrine in every 10,000 milliliters of total solution. Since we know that 1 gram is equal to 1,000 milligrams, we can also say there's 1,000 milligrams in every 10,000 milliliters of total solution, which can be simplified to 0.1 milligrams per milliliter. Lucky for us, they print both concentrations on the label, but in an anesthesia, we want you to understand what is meant by the ratio. It's advisable for you to memorize that a 1 to 100,000 solution is equal to 10 micrograms per milliliter, and that a 1 to 200,000 solution is equal to 5 micrograms per milliliter. I'd advise you to go back a slide and work out the math. 1 to 100,000 means there's 1 gram of epinephrine, or whatever the drug may be, in 100,000 milliliters of total solution, which can be simplified to 10 micrograms per milliliter. You will be using local anesthetic solutions often that contain epinephrine at a concentration of 1 to 100,000 or 1 to 200,000. So once you've proved to yourself that the ratio 1 to 100,000 is really equal to 10 micrograms per milliliter, it's advisable to memorize this. Proportions can be useful when the concentration is going to remain the same. Proportions are an equation between 2 ratios. The first ratio is set equal to the second ratio. The numbers on both sides of the equal sign closest to the equal sign are called the means, and the numbers on both sides of the equal sign furthest away from the equal sign are termed the extremes. There's always one term that's an unknown, represented by x. To solve a proportion, you multiply the means you multiply the extremes, you set the product of the means equal to the product of the extremes, and solve for x. Let's bring the tablet in here and say that the surgeon handed you a 1 milliliter vial of gentamicin which contained 80 milligrams. So in order to write that as a ratio, you could say 80 milligrams is to 1 milliliter, or 80 milligrams is to 1 milliliter. And what he wanted you to do was to draw up 35 milligrams of the drug to administer to the patient. So your other ratio is going to be 35 milligrams is to X milliliters, because it's the number of milliliters that you'll need to draw out of this vial that's your unknown quantity. We'll set these two ratios equal to each other, and now we have a proportion. The means are the two numbers closest to the equal sign on both sides, 1 milliliter and 35 milligrams. The extremes are the numbers on both sides of the equal sign furthest away, 80 milligrams and X milliliters. So multiplying the means, we have 35 milligrams. Multiplying the extremes, we have 80 milligrams times X. Solving algebraically for X, we divide both sides by 80. Bring in the calculator here. 35 milligrams divided by 80 milligrams is equal to 0.4375. So X is equal to 0.4375 milliliters. That was our unknown quantity. Up here we were solving for X milliliters. So ratios are useful when the concentration's going to remain the same. You're either looking for the number of milligrams or grams, or you're looking for the number of milliliters. If it's been a while since you've worked in scientific notation, you'll want to go back and refresh your memory on scientific notation. Remember, the number written before the multiplication sign is called the coefficient, and the number written after the multiplication sign is called the power. Multiplying with scientific notation is simple. You simply multiply the coefficients and add the exponents. Dividing in scientific notation is also simple. You divide the coefficients and subtract the exponents. It gets a little more complicated when you're adding and subtracting with exponents, because you first need to convert to the same power before you can do anything with the coefficients. In my addition example here, I have 7.58 times 10 to the 5th plus 2.871 times 10 to the 6th. You can't add those terms in that form. You need to first convert to the same exponents. So I've converted the 7.58 times 10 to the 5th to 10 to the 6th, which makes it 0.758 times 10 to the 6th. Now I can go ahead and add the coefficients, and the power remains the same. Similarly, you need to convert to the same power when you subtract with exponents. If you want the power to get larger, you move the decimal and the coefficient to the left. And if you want the power to become smaller, you move the decimal and the coefficient to the right. Your biochemistry instructor, Dr. Verrill, has recorded a nice video for you that demonstrates how to work with scientific notation in a Texas Instruments calculator. You'll want to get a scientific calculator and practice working with exponents and logarithms with your calculator before you start the program, so that we don't have to use class time to teach people how to use their calculators. This slide reviews the basic units of measurement within the metric system. The basic unit of length is meters and angstroms. The basic unit of mass is grams. For volume, it's liters. For force, the basic units are newtons and dynes. The basic units of energy are calories and joules. And watts are the basic units of power measurement within the metric system. These are the metric prefixes. You should be familiar with those that we use most regularly in medicine, which are milli, micro, centi, deci, and kilo. These are some basic conversions within the metric system. You'll want to make sure that you're able to convert within the metric system. And there are a couple of conversions you'll need to be able to do from the English to the metric system. They are the conversion of inches to centimeters and the conversion of pounds to kilograms. It's highly unlikely that your patient is going to give you their weight in kilograms. Most patients tell us their weight in pounds, but we dose our medications in anesthesia on their kilogram body weight. The next slide will give you a quick method of converting kilograms to pounds without having to use a calculator. You also will want to be able to quickly convert from feet and inches to centimeters and meters. This is useful when you're calculating a patient's body mass index. The second quick math tip is estimating a pediatric patient's weight. For instance, let's say you get a call from the emergency room saying that a 6-year-old patient is coming up for an emergency appendectomy. You will want to go into the operating room, set up your cart, and draw up medications based on what you estimate a 6-year-old would weigh. The quick and dirty formula for this is the patient's age divided by 2 plus 10 will give you the pediatric patient's weight in kilograms. So let's say that we have a 6-year-old coming up. Divided by 2, that gives us 3 plus 10. You will draw up medications based on an estimate that the patient will weigh 13 kilograms. There will be times where you'll find it useful to be able to estimate an adult patient's ideal body weight. We don't normally calculate our dosing in the obese population based on their actual weight. More likely we will use their ideal body weight or perhaps 20% above the patient's ideal body weight. So it's good to be able to have a quick reference to calculate what an obese patient's actual body weight should be, or their ideal body weight should be. The quick formula here for males starts with assigning 106 pounds for the first 5 feet, and then 6 more pounds for every inch above 5 feet. And for females, the formula starts with assigning 105 pounds for the first 5 feet, and then you add 5 pounds for every inch above 5 feet. So to demonstrate this, let's say that we have a male patient who is 5 feet, 10 inches tall. We're going to assign 106 pounds for the first 5 feet, and then we're going to assign 6 more pounds for every inch above 5 feet. And he's 10 inches above 5 feet, so that's 60 more pounds. Adding these together, his ideal body weight should be somewhere around 166 pounds. And now from the last slide, you know how to quickly convert that into kilograms. Unfortunately, the medical and scientific community can't get together on a single unit of pressure measurement. They can't even agree on a couple of units of pressure measurement. So as anesthesia students, you will see all of these pressure measurements, and you need to be familiar with them. Each one of the units here is a measurement of pressure. They're all equal to atmospheric pressure at sea level, and they're all equal to each other. So you will want to commit these to memory and be able to convert between each of these different units of pressure measurement. Your patient's blood pressures are measured in millimeters of mercury. Their breathing pressure in the anesthesia breathing circuit is measured in centimeters of water. There are medical gas cylinders attached to the back of your anesthesia machine. They measure the pressure in the cylinder by a gauge which reads pounds per square inch. All the rest of these units you will see either in the anesthesia literature when you're reading the literature, and or you may use them in your chemistry and physics course. This is a very common calculation that you will use in the clinical area. These are the formulas for calculating the correct size endotracheal tube for pediatric patients. These are the formulas that you learned when you took PALS. For choosing the correct size of endotracheal tube in a pediatric patient, when the tube is uncuffed, the formula is the patient's age divided by 4 plus 4. If you're using a cuffed endotracheal tube, the formula is the patient's age divided by 4 plus 3. And the depth at which the tube should be taped at the patient's lip is given by the formula the patient's age divided by 2 plus 12. Hurley Medical Center and many of our clinical affiliate partners do bariatric surgery. When doing bariatric surgery, it's not uncommon for the patient's body weight to be expressed in terms of body mass index. The formula for body mass index is the patient's weight in kilograms in the numerator, the patient's height taken squared in meters in the denominator. You will want to memorize this formula. A body mass index between 21 and 25 is considered an ideal body mass index. A body mass index between 26 and 30 is considered an overweight patient. Between 31 and 35, the patient is considered to be very overweight, and above 35 is the definition of morbid obesity. Here's a practical example, another clinical scenario. You finish a case and need to transport the patient to the neurotrauma intensive care unit. You go out to get an oxygen cylinder and you find that the pressure gauge is not showing you that the tank is completely full. The pressure gauge reads 1,200 pounds per square inch. Your instructor will want you to be able to tell them how many minutes of oxygen you will have available to transport the patient to the neurotrauma intensive care unit at a liter flow of, let's say, 10 liters per minute by AMBU. How will you calculate this answer? Well, in order to calculate the answer, you first need to know the measurements in a full E-cylinder of oxygen. An E-cylinder just describes the size of the oxygen tank. Those oxygen tanks that we frequently use in the clinical area are considered E-cylinders. A full E-cylinder will register 2,000 pounds per square inch pressure on the gauge, and when open to atmospheric pressure will emit 660 liters of oxygen. So, since your cylinder only reads 1,200 pounds per square inch, you need to know how many minutes you're going to have to get your patient transported to the neurotrauma unit. How do we do this? Well, we start out by putting in our 1,200 pounds per square inch pressure, and then we're going to put in the conversion factor. We know that a full E-cylinder will read 2,000 pounds per square inch and will contain 660 liters. Setting this up this way, I'm able to cancel pounds per square inch units in the numerator and pounds per square inch units in the denominator. The only units that are left are liters, but liters are not what I'm looking for. I'm looking for minutes, so I need to go back up into the story problem and get another factor, and that factor is the liter flow on the AMBU bag. We're going to use 10 liters per minute. This allows me to cancel liters in the numerator, liters in the denominator. The only units I have remaining are minutes, and minutes are what I'm looking for in the answer. Therefore, I know that my equation is complete. So now we just need to bring in the calculator and crunch the numbers. You multiply the numbers in the numerator, 1,200 times 660, and then you divide by all the numbers in the denominator. So we'll divide by 2,000, and we'll divide by 10, and that tells us that we have 39.6 minutes to transport this patient to the neurotrauma intensive care unit with this tank that reads 1,200 pounds per square inch pressure if we run the oxygen liter flow on the flow meter at 10 liters per minute. You will be asked to calculate your patient's FiO2. Anesthesia machines have 3 flow meters: an oxygen flow meter, an air flow meter, and a nitrous oxide flow meter. Obviously, if the oxygen flow meter is the only flow meter that you have dialed on, then the patient's receiving 100% oxygen or 100% FiO2. But it's not often that we run 100% oxygen through an entire case. Normally, we will run oxygen and nitrous oxide or oxygen and air. So depending on the liter flow and the gases that you have turned on, you need to be able to calculate what FiO2 you're delivering to your patient. My first example here shows that the oxygen flow meter is dialed to 2 liters per minute, and the nitrous oxide flow meter is also dialed to 2 liters per minute. What goes in the numerator is the number of liters of oxygen available to the cells to be used in cellular respiration. So all of the oxygen dialed in from the oxygen flow meter is definitely oxygen that's usable by the cells. but the oxygen in the nitrous oxide is chemically bound to the nitrogen and not available to the cells for use in cellular respiration. So the formula is the total oxygen available to the cells in the numerator, the total flow in the denominator. So in this case, only the 2 liters from the oxygen flow meter are available for cellular respiration, so we put 2 liters in the numerator. The total flow is the amount you have dialed in, 2 liters of oxygen plus 2 liters of nitrous oxide, goes in the denominator. 2 liters divided by 4 liters times 100 to make it a percent tells us that we have dialed in 50% FiO2 when we have the oxygen flow meter at 2 liters per minute and the nitrous oxide flow meter at 2 liters per minute. It gets a little bit more complicated when you're running oxygen and air. Obviously, all of the oxygen that you dial in is available to the cells, but 21% of the air that you dial into the air flow meter is also oxygen that's available to the cells. So in this case, the numerator gets a little more complicated. I put in 2 liters for the entire volume coming from the oxygen flow meter, and I added to that 21% of the gas coming from the air flow meter is actual oxygen that's available to the cells for cellular respiration. So in this case, we do 21% times 2 liters, add that to the 2 liters coming from the oxygen flow meter, divide by the total flow, times 100 to make it a percent, and the FiO2 becomes 60.5% when we have the oxygen flow meter on at 2 liters per minute and the air flow meter dialed to 2 liters per minute as well. It occurs to me that you might not be familiar with the factor dimensional method of problem solving. This is the method that I was using in the oxygen cylinder slide, where I was lining up the units so that I could cancel units in the numerator and the denominator. If you're not familiar with this method, I think you'll find it quite helpful, particularly if you're a student who doesn't like math and doesn't like story problems, because you never know how to set up your equations to calculate your answers. So here is a very common clinical scenario where you can use the factor dimensional method of problem solving. Your instructor hands you a vial of propofol and a syringe. She tells you that the patient's weight is 155 pounds and asks you to calculate how many milliliters of propofol you will administer to the patient. So let me demonstrate how you use the factor dimensional method of problem solving for this. The first thing you need to do is go into the story problem and pull out the factors that are given. We know that the concentration of propofol is 10 milligrams per milliliter. We know that the dose that we want to administer our patient is 2 milligrams per kilogram, and that the patient's weight is 155 pounds. You're also going to need to draw from your memory the conversion factor from pounds to kilograms that you memorized in an earlier slide. The key to solving problems with the factor dimensional method is to start out by considering what you're looking for in the way of units in your answer. And what we're looking for here is the number of milliliters. So I always start by writing equals and then milliliters. Then you go into the factors that are given and start plugging things in so that you can cancel units in the numerator and units in the denominator, so that when you're all finished, the only units that remain are milliliters, and milliliters are going to have to fall in the numerator. Always, if there's only one unit in the answer, it needs to be in the numerator. So let's go up into our givens. Where do we see milliliters? Right here, 10 milligrams per milliliter. We know that the milliliters needs to be in the numerator. All right. We know that there are 10 milligrams in every milliliter of propofol. How is it that we can insert this factor upside down? Up here, the milligrams are on the top and the milliliters are on the bottom. Well, it's because this entire factor is equal to 1, meaning if you give 10 milligrams of propofol, you're also giving 1 milliliter of propofol. Every time you give 1 milliliter of propofol, you're giving 10 milligrams of propofol. So they are equal to each other, which allows you to insert it into the equation upside down or right side up. All right, so now we have the milliliters in the numerator, but we have milligrams in the denominator, so we need to go up here and find something that's going to allow us to cancel milligrams, and here it is. 2 milligrams per kilogram. Now I can cancel milligrams in the numerator and milligrams in the denominator. My milliliters are still in the numerator, but I have kilograms in the denominator, so I'm not finished. I need to go up here and find kilograms, and what I'm going to need to use is the conversion factor that I know. There are 2.2 pounds in every kilogram. Notice I put this in with the kilograms on the top, but if I needed to, I could have put the pounds on the top, because 1 kilogram is always equal to 2.2 pounds, so the entire factor is equal to 1. Now I can cancel kilograms in the numerator and kilograms in the denominator. I have pounds now that I need to get rid of. How am I going to get rid of the pounds? I'm going to go and pull down the patient's weight. We know that the patient weighs 155 pounds. I can cancel pounds in the numerator and pounds in the denominator. This factor, saying 155 pounds in the numerator, is the same as saying 155 over 1. If I had inverted this factor, you would be saying that the patient weighs 155th of a pound, which we know is not correct. So when you're entering a factor that only has one number, you need to make sure that you consider what you're saying by inserting that factor either in the numerator or in the denominator. So I've canceled pounds, I've canceled kilograms, I've canceled milligrams. The only units remaining are milliliters, so my equation is complete. I now can bring in the calculator and do the math. 155 times 2 divided by 2.2 divided by 10 tells me that I will administer 14 milliliters of propofol to induce my patient's anesthetic. Here's another medication calculation where the factor dimensional method works quite well. You have dopamine, 400 milligrams, and 250 milliliters of D5W. Your patient weighs 198 pounds. You wish to infuse the dopamine at 5 micrograms per kilogram per minute. At what rate in milliliters per hour will you set the infusion pump? Let's bring in the tablet and figure this out. Remember, we start by considering what units we're going to want in the answer. And in this case, we want milliliters per hour, with milliliters in the numerator and hours in the denominator. Now we go up into the story problem and start pulling down factors and lining up units. We have 400 milligrams in every 250 milliliters. That puts milliliters in the numerator where we want them. Now, there are no milligrams in our story problem, but we know the conversion between milligrams and micrograms are there. So we know that every 1 milligram is equal to 1,000 micrograms. That allows me to cancel milligrams in the numerator and milligrams in the denominator. Now I have micrograms that I need to get rid of. Well, we want to infuse dopamine at 5 micrograms per kilogram per minute. When you say per, that means that the next factor is going in the denominator. 5 micrograms per kilogram, 5 micrograms per minute. Both kilograms and minutes go in the denominator. This allows me to cancel micrograms in the numerator and micrograms in the denominator. Now I have both kilograms and minutes in the denominator that I need to eliminate. So I can go up here and find my patient's weight, which is in pounds, so that I know I'm going to need to use my conversion factor. There are 2.2 pounds and 1 kilogram. Now I'm canceling kilograms. I also need to cancel these minutes. I need them to become hours. So there are 60 minutes in 1 hour, something you just draw from your memory. Now I'm canceling minutes in the numerator and minutes in the denominator. I have milliliters in the numerator. That's what I'm looking for in the answer. I now have hours in the denominator, also what I'm looking for in the answer. But I still have these pounds, which I don't want in the answer, so I'm not finished setting up my equation. I need to go in and find something in the story problem to cancel pounds, and it is the patient's weight, 198 pounds. Remember that the patient's weight here needs to go in the numerator, 198 pounds over 1. Canceling pounds. Now the only units I have left are milliliters in the numerator, hours in the denominator. My equation is complete. The next thing you do is bring in the calculator. You multiply all the numerators, divide by all the denominators, and you have the correct answer. 198 times 60 times 5 times 250 divided by 2.2 divided by 1,000 and divided by 400. Tells me that I'm going to set my infusion pump at approximately 17 milliliters per hour to deliver 5 micrograms per kilogram per minute to this 198-pound patient from a dopamine concentration of 400 milligrams in 250 milliliters. We're coming to the end of the math tutorial here. I'll work one last problem for you. This seems to be the type of problem that gives students the most trouble. You have a 30 milliliter vial of Marcaine 0.5% with 1 to 100,000 epinephrine. You need Marcaine 0.35% with 1 to 100,000 epinephrine. What will you add? When you're working these problems, you need to first recognize that you're working with 2 separate drugs. Each drug needs to be worked out individually. So I'm going to start by working with the Marcaine alone. The original vial of Marcaine has some mass of drug, some volume, and a concentration. What is known? We know that the vial contains 30 milliliters. We know that the concentration of Marcaine is 0.5 grams in every 100 milliliters. We learned previously what that percent sign means. Now you could work with grams all the way through this problem, but I have a tendency to like to work in milligrams, so I'm just going to do one extra little conversion here. I know that there are 1,000 milligrams, that's milligrams, in every gram. That leaves me with milligrams in the numerator and milliliters in the denominator. Bringing in the calculator, 0.5 times 1,000 divided by 100 tells me that there are 5 milligrams per milliliter. The concentration is 5 milligrams per milliliter in the original vial, and we're just talking about the Marcaine here. Whenever you know 2 of these factors, mass, volume, and concentration, you can calculate the third. So I'll go up here and calculate how much mass of drug is actually in this original vial. 30 milliliters at a concentration of 5 milligrams in every milliliter allows me to cancel milliliters and come up with the mass of drug in milligrams. So I have 30 milliliters times 5, or 150 milligrams of Marcaine drug in the original vial. Now you go up and look at what the question is asking. The question is asking, you need Marcaine 0.35% with 1 to 100,000 epinephrine. So that was what was in our original solution. What's going to be in our final solution? Again, there's going to be some mass of drug, some volume, and some concentration. What have they given us? They've given us the new concentration, which is 0.35 grams in every 100 milliliters. And since I'm working in milligrams, I'm going to say that there are 1,000 milligrams in every gram, which allows me to cancel grams, and gives me the answer in milligrams per milliliter. Bring in the calculator, 0.35 times 1,000 divided by 100 tells me in the final solution we want the concentration to be 3.5 milligrams per milliliter. All right, now you need to stop and think about this. Are you going from a more concentrated solution to a less concentrated solution, or from a less concentrated solution to a more concentrated solution? We're going from 0.5% marcaine to 0.35% marcaine. So we're going to a more dilute solution. That means I'm going to add volume. I'm not going to add any more drug. Therefore, this factor is just going to come over here. We're not changing the amount of drug. We're going to change the volume. When you know two factors, you can calculate the third. 150 milligrams times 3.5 milligrams in every milliliter allows me to cancel milligrams in the numerator and denominator. We'll bring in the calculator. 150 times 1, actually, divided by 3.5 tells me that we need 42.9 milliliters in my final solution. So the question is asking, what would you add? This seems to trip students up too. They're able to calculate what's in the original vial. They're able to calculate the mass, volume, and concentration of the final solution, but they forget the last step means to go up and answer the question that's asked. The question that's asked is, what will you add? The original solution contained 30 milliliters. The final solution needs to contain 42.9 milliliters. We know that we're adding diluent or diluent because we're going to a less concentrated solution. So 42.9 milliliters in the final solution minus the 30 milliliters that we had in the original solution tells us that we're going to add 12.9 milliliters of normal saline or D5W or whatever your diluent is. That's how you correct for the marcaine. Okay, now that we've corrected the marcaine, we need to work on the epinephrine. Remember that we added 12.9, that's a decimal, 0.9 milliliters to the solution when we corrected the marcaine from 0.05% to 0.35%. So now our epinephrine original solution has a mass, volume, and concentration. The concentration was 1 to 100,000, which we know means 1 gram in every 100,000 milliliters. And just to be consistent, I will convert to milligrams, because that's what I did with the marcaine. There are 1,000 milligrams in every gram. Many people, whoops, I didn't mean to cancel out the milligrams. Many people would work in micrograms here. 1,000 in the numerator divided by 100,000 in the denominator gives us 0.01 milligrams per milliliter. The original vial contained 30 milliliters, so now we can calculate how much epinephrine drug was in the original vial. 30 milliliters times 0.01 milligrams per milliliter allows us to cancel the milliliters and gives us the amount of drug in the vial. 30 times 0.01. The original vial contains 0.3 milligrams of epinephrine drug. So what do we want in the terms of epinephrine in the final solution? Again, there will be a mass, a volume, and a concentration. The problem says we want the concentration to remain 1 to 100,000. So we can take this term and just transfer it over here. 0.01 milligrams in every milliliter. Remember that we added 12.9 milliliters to the original solution when we corrected for the Marcaine. So we now have 42.9 milliliters in our solution. When you know two terms, you can calculate the third. 42.9 milliliters times 0.01 milligrams per milliliter allows me to cancel milliliters, tells me how many milligrams I need in the final solution. 42.9 times 0.01 tells me that we need 0.429 milligrams in the final solution. So we added diluent to correct the Marcaine, and now we're going to need to add some epinephrine drug back into the solution in order for the epinephrine concentration to remain the same. Again, don't stop here. You need to answer the question that's asked. What question is asked? What will you add? We had 0.3 milligrams of epinephrine in the original solution. We need 0.429 milligrams of epinephrine in the final solution. So don't forget to do this last step, which is subtraction. 0.429 minus the 0.3 that we had in the original solution. We will add 0.129 milligrams of epinephrine in order to correct back to 1 to 100,000 concentration after we diluted the solution to correct the Marcaine concentration. We've come to the end of this math tutorial video. I hope that you found it helpful. I hope you'll take some time over the summer to work on these problems and make sure that you're proficient at them before you start the program. It will save you time, and time is a precious commodity in your first semester. Also, take the time to look at Dr. Verrill's video on how to use a Texas Instruments calculator with scientific notation and for performing logarithms. I look forward to meeting you and working with you in the fall. Thank you for listening.